Welcome back to Physics 246 Online. We're going to finish up the last section in Chapter 7 today, dealing with what we do if the data that we measure are expected to follow a fitting function that is a nonlinear function. And the technique that we'll outline works in some cases when we can take a simple nonlinear function and perform an algebraic operation on that equation to transform it into a linear equation that will be something that we can analyze using the least squares fit techniques that we've already considered. Now first, what do we mean by nonlinear? We mean that it's nonlinear in the coefficients that we're trying to determine the values of when we do the fit. A linear function is one where those coefficients only appear as multiplicative constants in the terms of the fitting function. But there are some fitting functions where those coefficients might appear in other places, and that's what makes them nonlinear. So here's an example. What if we have a set of xy data that we've measured, and they are expected to obey this sort of exponential function that we have seen in many cases in physics and engineering applications? So there's a constant c, and then the other constant is lambda, which appears in the denominator of the exponent. So we would like to find the values of c and lambda and their uncertainties that provide the best fit to the measured data. And here, clearly, the lambda is not a linear term because it doesn't appear as a simple multiplicative constant outside of the function, the way that the c does. So what do? Well, we try to linearize this function by doing some kind of mathematical operation on it that will make the term, in this case, the lambda term that's in the exponent, come down and appear in a simpler place. So you probably recognize that if we take the natural log of both sides of this equation, it becomes log y equals log of c plus 1 over lambda times x. And what we've now done, the lambda now is no longer in an exponent of our term, but it appears as a simple multiplicative constant, although it's in the denominator in this case. So when we compare this to the equation of a straight line, we can match up the terms and see that on the y-axis, we could call this log y term y prime. And then we would also see that the constant b would correspond to this term log of c because it's a constant and doesn't depend on the variable x. And finally, x would be exactly the same as x prime that's in this linear equation, where the constant a out in front, the slope term, would simply be 1 over lambda. So if we perform this fit using our standard least squares methods, we would get an error in a and an error in b, we'd get values of a and values of b that we could then use to calculate lambda and c along with their errors. So the point is that in this case we would plot log of y on the y-axis and x on the x-axis, and if the data obey this equation, we'd get a straight line. However, there's one matter left to consider, because when we do the original measurement, for different x values, we measure y, and there's going to be some uncertainty in the value of y that we measure. Nevertheless, y is not one of the terms that we use in our fit. So what we really need to do is find how the errors in y get converted into errors in y prime that appears in our new transformed fitting function. That's not too difficult though, because y prime is just equal to the log of y. So if we have errors in y, we can easily use methods that were developed in Chapter 3 to calculate the errors in y prime. So for example, this is equation 313, and it shows that the errors in y prime would be related through this simple equation to the errors in y. And all we really need to do in order to complete this process is calculate that partial derivative. So the partial of y prime with respect to y is 1 over y. And then when we take the square root of both sides of this equation, now from our originally estimated or measured uncertainties in y, we would just divide each of those by the y value to get the uncertainties in y prime. And that, when we do the linear least squares fit, that would then give us values of the parameters c and lambda along with their errors that would be the correct values. So just remember in cases like this where you do some kind of mathematical operation to transform the fitting function, you may also need to transform the uncertainties. Let's look at a couple of different examples in closing this section. One simple one might be the following case. If we measure data y as a function of x, but we have reason to believe from theoretical considerations that the data should follow an equation like this, where y is proportional to x cubed, and there might be some constant value, well, we compare this to the equation of a straight line and see that it's almost the same. The y prime is the same as y, and the only difference here is that in place of x prime, we have x cubed. And so the point is here that if we simply plot the y value as the y prime versus x cubed acting as the x prime, we should get a straight line if the data obey this equation. And of course, the a value and the g value are the same, the b value and the h value are the same. And in this case, you can ask yourself whether we would need to transform the uncertainties in y, and the answer is no, because y prime is the same as y. So whatever the errors are in the y values, they are the same errors in the y prime values. So that becomes a pretty simple case. A more complicated one, although we see it quite often in physics, is where the y value is expected to depend on x through some kind of power law dependence, where k and n are the coefficients that we try to find the values of. Once again, in order to get the coefficient out of the exponent, taking the natural log of both sides accomplishes the task. So this becomes log of y equals log of k plus n log of x. And once again, we compare this to the equation of a straight line and can identify very quickly that y prime is log of y, that x prime is log of x, and that the coefficient, or b, that the intercept b, is the same as the log of k. And so in this case, we would need to transform the errors because the errors in y would not be the same as the errors in y prime, but we already showed how to do this kind of thing on the previous slide. So once we transform the uncertainties, we would be ready to do the least squares fit, and we would obtain values for b and its error that could be converted into values of k and its error, and then we would get a value of a and its error, which would be the same as the value of n and its error. So these are pretty straightforward techniques. They are not useful for every kind of nonlinear function. In particular, we will find there can be cases where we have, on the right-hand side, we have sums of terms like this. And in that case, we can't easily just take the natural log of both sides to linearize the function. We'll have to use more sophisticated techniques. But this method is still quite often useful, particularly when we have simple forms of nonlinear functions. So, we're done with Chapter 7, and I will see you in class.